Okay, welcome everyone. So it's a pleasure to have Professor John Peacock over here to give a new lecture course on large-scale structures as a cosmological probe. I don't have much to say except that if you have read the book, the man is over here, so you should, and if you have the book, probably you could get it signed also. So I'll just leave it to John. John, thanks for coming.
Okay, thank you. Hello, everyone. It's really nice to be here in this beautiful place. I haven't been here from the start, but I gather you've had a lot of lectures about perturbation theory, which I'm sure you loved, yeah? Anyway, so you know a lot now about the development of irregularities in a perturbed universe as far as the evolution of the mass distribution is concerned. So the job I've been given is to talk about how you confront that theory, that window into the early universe, with the data that we have on the galaxy distribution. So this is the raw material, the large-scale structure of the universe. And this beautiful picture looks like a computer simulation, but it's not. It's the real cosmic web of which we're part. So it's where we came from, and we need to understand it and what we can learn from it. So there are two parallel tracks that the study of large-scale structure leads you to. You can be a fundamentalist. That is, you can say, I don't really care about astrophysics, but I do care about issues like the overall mass content of the universe, how much dark matter there is. I care about the properties of the vacuum energy, or whatever it is that's making the universe accelerate in its expansion. I care about whether gravity is correctly described by Einstein's relativistic theory, and I care about whether the primordial fluctuations were a simple Gaussian field or something more complicated. The trouble is, you can't ignore astrophysics, so the whole issue of how the observed galaxy distribution that we see relates to halos of dark matter is something that we have to understand in detail in order to interpret the data. And that leads us to make sure that our fundamental inferences are correct, to want to understand subtleties of how the properties of galaxies depend on their cosmic environment within the cosmic web. So I'll try and cover issues from both these columns. So this is the basic plan. I've got 4 lectures, so it's in 3 parts, which doesn't mean you get 1 lecture off. The first 2 lectures probably cover this set of basic tools here about how we approach statistically describing the galaxy perturbations. And then tomorrow I'll have 2 lectures, each on particular aspects of frontier research in large-scale structure, using the so-called baryon acoustic oscillation signal to measure the distance scale of the universe, and trying to observe the peculiar velocity field in the universe as a probe of theories of gravity in the second lecture. So today, the 2 lectures, I'm going to be covering this material. So I will say a few things. I mean, it's partly a historical approach. This is cosmology of the next decade, but this is, to some extent, cosmology of the last 2 or 3 decades, because I think it's important to understand how we got to where we are, and also to build up right from the primordial state of ignorance that used to exist in the field, how the key tools that we now use were arrived at. So I hope that some of this will be familiar to some of you, but I hope it's interesting to go through the entire history of the development of these ideas. I would say, please do stop me with questions if you want points here expanded. It's much better we go in some depth into a few topics than just skate over a whole pile of them. All right, that's the health warnings out of the way. Let's begin with the statistical approach then to the clustering of galaxies. And our first problem is that galaxies are pretty well points, discrete points on the sky, whereas everything that we talk about in perturbation theory governs a continuous field of matter. So we've got to figure out how we're going to handle that statistically. And this is the raw material, or at least as it started out. if you were doing cosmology in, say, 1960 with the galaxy distribution, you might have had this fine map, which was made by Shane of Vitanen, looking at photographic plates over the space of several years, counting galaxies by hand. And if you ever think you're working hard by staying up late at night debugging your Python, spare a thought for what these guys used to get up to. So when you just see a distribution of points on the sky, what do you do? Well, what has commonly been done, and it's still an approach that we use today, although, as you will see later on, it's not strictly correct, we apply a thing that is called the Poisson clustering hypothesis. What does this mean? It means that we assume that there is some field in the universe delta fluctuating as a function of x. And what is delta? It really tells you the probability of getting a galaxy at a given location. And so the hypothesis is that the actual galaxies that we get can be thought of as just a Poisson process with this as the expectation. So let's start, first of all, by reminding ourselves of the statistical tools that we'd use to talk about a fluctuating underlying density field then. And this has all been rehearsed already, but let's just go over it again in notation that I will use. So first of all, we're going to be expanding the density perturbation in Fourier space as a sum of plane waves, and the Fourier coefficients we get by taking the density field, multiplying by another plane wave, and integrating. Integrating over what? There's a problem with the universe when it comes to Fourier analysis, which is that the universe is infinite as far as we know. So the sensible way to approach this is by a normalization box where we make periodic extensions. And the volume that we're choosing to repeat in this way will eventually go to infinity. But personally, I find it very helpful in doing these analyses to keep it explicitly set as some value, because you know in the end that the V has to disappear. And when it does, that tells you that you've done something right. So let's take this. This tells you something important about the allowed values of the wave number. Say kx is just some multiple n of 2 pi divided by the size of the box. So those harmonic boundary conditions are useful in a lot of these manipulations. So for example, supposing we were interested in the autocorrelation function of the density field, all we have to do is to take the Fourier expansion here, multiply it by itself twice, with the spatial coordinate offset by some amount, and that sum generates a whole pile of terms which know about the difference to your wave vectors. And because of the periodic boundary conditions, the volume average of that is 0. So all the cross terms drop out, and you conclude that the correlation function is indeed just the Fourier transform of the modulus squared of the Fourier coefficients, that is, the power spectrum. And if you want to take the continuum limit, you would say I would introduce a factor 2 pi, v on 2 pi cubed. That should be a very familiar combination to you. Somebody remember what it's called? No? Density of states. Okay, so v volume of the box divided by 2 pi cubed times the volume element in wave number space is the numbers of modes that live in a particular region of K-space. Okay, so we're just replacing this, this discrete sum here by an integration over K-space with the density of states. And it's convenient to combine a lot of these different factors together into this dimensionless power spectrum here. Big delta squared, which brings in the arbitrary volume element with the power spectrum itself with k cubed by k cubed, because the volume element is k squared dk, or k cubed d log k. So in other words, the variance in the density is then just thought of as an integral over log scale of delta squared. That's what the dimensionless power spectrum means. It's contribution to the variance per log k. All right, so the autocorrelation function of the density field has a counterpart in Fourier space. You can think about saying what is the product of two Fourier modes of different wave vectors, k and k prime. For that, you just need to take the definition of the Fourier transform here, multiply it together twice, and that will give you two different spatial coordinates, x and x prime, say. But if you express x prime as x with some offset r, then you can write the pair of integrals in this form. And what you now do is take an ensemble average. So the ensemble average comes inside the integral and goes around the deltas. So ensemble average of delta of x plus r is what we mean by the 2-point function, the function of r. And it's only a function of r, that is, it doesn't depend on x any longer. So what we would say here is that the 2-point function is translationally invariant. In other words, it doesn't depend, yeah. No, everything, good, thank you for asking that. I haven't got to Poisson yet, I'm afraid. All I'm doing is revising the statistical tools that we'll use to describe the continuous generating field from which the galaxies will be driven, will be chosen, okay? So we're almost at the point where I can introduce Poisson sampling. So because this is purely a function of r, then this integral can be done directly. That just gives us the correlation function. This one here, again, if k and k prime are different because of the boundary conditions of the periodic volume, this integral will vanish unless k is equal to k prime, in which case you get a factor of v. And so you can end up saying the 2-point function in Fourier space is just the power spectrum times a Kronecker delta of k and k prime. And that's a much easier way of approaching it than the common formula you'll see, which is to say that this in the limit becomes proportional to a delta function. You'll get 2 pi cubed times the power times a Dirac delta in k space. But it's the same thing. All right, notice there's two different averages here. In the first step, I just took an average over the volume. Here, I took an ensemble average, that is, different realizations of the statistical process within the volume that make the density fluctuations. In practice, these are normally very close, and formally they become equivalent as the volume tends to infinity. And this is what we mean when we say the statistical process is ergodic. And it's a good job this is true, because theory gives us ensemble average quantities observations give us volume average quantities. And so these two have to be the same, otherwise we couldn't do science. All right, now let's imagine that now we don't have a continuous density field, we have just the distinct galaxies. How are we going to compute Fourier coefficients? Well, the Fourier coefficients derive, now we're not Fourier transforming the continuous density field, we're transforming the number of galaxies that we actually have. So that defines a density field that's just a superposition of delta functions. But the nice way of treating this is to split space up into a large number of very small cells. So one of these cells will occasionally have a galaxy in, most of them are empty. So this is nice. So you can basically say that n is 0 or 1, and 2 and higher can be neglected if you make the cells small enough, which has the nice property that n squared is equal to n. You can exploit that if we want to work out the power spectrum. So let's start with pure Poisson sampling. So I won't put any large-scale structure in yet. I'll just distribute galaxies at random throughout space. So now the Fourier coefficient, I'm just Fourier transforming the numbers in each microcell. And if you think about this, so the Fourier factor here is just a phase. And if the points are put down at random, that phase is also random. So the complex amplitude on the Argand diagram actually just undertakes a random walk. Think of the real and imaginary parts of delta K. It just takes steps of a given size, dictated by the number, but of a random direction. And we're just interested in the length of that random walk. So that's very easy. We just add up the variances of the individual contributions. That is the sum of the n squareds. But because n squared is the same as n, all we're doing is adding up the total numbers. So we conclude that the power spectrum, the Poisson process, is just 1 over the number of objects. So there's a problem in the literature, which let me try and clarify here. You will frequently see these two quantities, that is the modulus squared of the Fourier coefficients and P, both called the power spectrum. But they are not the same. The reason is that, as you can see, let's say from this defining equation here, delta is a dimensionless quantity, so the Fourier coefficients are dimensionless as well. But in the literature, you'll usually find that P has dimensions of volume. Why is that? That's because P is actually the normalization volume times the dimensionless power spectrum. The dimensionless power spectrum that is the one of fluctuations per log K. The mod delta K squared is also dimensionless, but not the same quantity as this. But it's the combination with the volume that we are normally interested in. And so the shot noise power is just 1 over the number density. That's the key bottom line. So that's for a pure random distribution. If I now try and have everything, I would say the number in each microcell is the expectation number, which comes from the density fluctuation delta, modulated by, the global expectation number modulated by the density fluctuation plus a Poisson fluctuation. And if you analyze that model, putting in both the ensembles, that is, averaging over a Poisson ensemble, so that the average of this is 0, and averaging over the density fluctuations, you'll conclude the bottom line, which is the power spectrum is the power spectrum of the smooth generating density field plus the power spectrum of shot noise, this discreteness correction. And the only reason this is there is kind of obvious, is because if you have a point process if you ask what the autocorrelation of that point process is, then whenever the points overlap, you have a delta function. And that delta function seems unphysical to you, so you want to subtract it and analyze what remains. And if you subtract the delta function from the correlation function, you're subtracting a constant from the power spectrum. Okay, so I'm sorry that was very well known to the majority of you, but I thought one may as well start with the real basics. So, when people first started doing galaxy clustering, it was taken for granted that this field that the galaxies were Poisson sampling was just the mass field. And this isn't a stupid thing to assume. And indeed, it's the way things would be if galaxies formed very early in the universe. And you can see this by a nice argument that was given by Jim Fry in 1996, when people were first wrestling with the concept of biased galaxy formation and wondering if the degree of bias could be large. And all he said was that imagine some galaxies in a given volume of space, and imagine there's gravitational collapse, so that volume shrinks, containing the same number of galaxies. What happens to the density fluctuation? Well, it starts off at some initial value, and so the density is 1 plus delta times the mean. If the volume then shrinks, the density fluctuation would just be scaled. The initial value times the final volume divided by the initial volume. You're just conserving galaxies. And we're assuming that the transformation of volume is the thing that's dictating the mass fluctuations. As you've seen, at least I hope, somebody has talked at length about the cosmic displacement field. Is that true? Okay, let's just say a few words about that. You start off with a uniform set of points. You move them with some displacement, call it d. It's not hard to show that the density fluctuation you make is minus the divergence of that displacement field. So whenever there's a density fluctuation, it's because particles are moving together. So assume they all move, and therefore we just need to know how much the mass fluctuation inside the sphere has changed, and that tells us how the overall fluctuation is altered. So let's linearize that, take delta to be small. You will find that the final density fluctuation in the galaxies is the initial one plus the change in the matter one. And of course, the change in the matter one is driven by the growth factor of density fluctuations. So as you let the scale factor grow, the growth factor becomes large. The dominant term here is just whatever the mass fluctuations at the early times were times the growth. In other words, gravitational collapse would drive the galaxy fluctuations to be the same as those of the mass, whatever they were initially. It sounds quite reassuring, but the trouble is, as the data poured in, and we were able to measure the amplitude of galaxy clustering for different galaxy types, it was clear that the amplitudes were different. So this argument couldn't apply to all galaxies. All right, so we need a more general framework for the relation between light and mass. And the first thing that you would reach for is what's called local bias. That is, the idea would be that the fluctuation in the galaxy field would be some function, and this function encodes the whole complexities of galaxy formation of the mass fluctuation. And obviously you can linearize that around delta equals 0, and there will be some linear response B, and that's the linear bias parameter. And so from this point of view, B is just some quantity to be determined empirically if you don't have a theory for galaxy formation. Sorry, say that again. How do you go from local to local? Well, this is just saying density in the galaxies versus density in the mass is something, right? And there will be a point close to the mean density. It is delta equals 0. And so it's just the tangent at that point. You're simply differentiating the function. And so, of course, you can use a Taylor series. And it's very common, very common in literature to have a 3-term Taylor series, including a linear term and a quadratic response. Why is the constant term there? The answer is that delta equals 0 always defines the mean density. So if you take a nonlinear function of the mass density as you are here, these two terms, well, that one has an average of 0, this one has non-zero average, so you need a constant to subtract it. Now, if you're going to work with a more complicated expression like this, though, well, actually, even with the simplest linear expression or a more complicated nonlinear one, there's a problem. And this, Aseem mentioned this earlier, that you have to have a physical density result from all of this. That is, the density fluctuation has to be greater than -1. And I don't know if anybody realized, actually, because yesterday, you remember Aseem showed this nice picture where you took a large-scale structure and you kept the amplitudes of the Fourier modes the same, but scrambled the phases. Yes? Now, the trouble is that looks quite impressive, but physically it's meaningless, because as soon as you scramble the phases, you'll make a Gaussian density field, which is therefore positive and negative deltas extending, and the Gaussian extends to delta equals -infinity. So that picture actually had negative matter densities in it. Okay, and physically we can't have that. So you need some model that allows you to work with a density field that's non-linear, but still of positive density. And there's a very nice and informative model that was introduced by Bowles and Bernard-Jones of the log normal field. So what you do here is say, I'm going to generate a density fluctuation starting from a Gaussian process of 0 mean and some variance, sigma squared. You just exponentiate the fluctuation you first thought of with an offset to ensure that it's correctly normalized, and that gives you a new density process. And the beautiful thing about this is that all the statistics of this nonlinear field can be calculated. So, for example, suppose we were interested, having made this transformation, in the 2-point correlation function of the new delta. Well, we know the joint distribution for the by the way, I don't know if has anybody actually said what is a Gaussian process. A Gaussian process is one where you define n points in space, as many as you like, and they each have different density fluctuations. But the joint distribution of all those densities is a multivariate normal. That's the definition of a Gaussian density field. So it's not just that the distribution of density at one point has a Gaussian probability distribution. So for 2 points, delta 1 and delta 2, with some separation, we need the covariance matrix for the multivariate normal. The covariance matrix is very simple. It's the off-diagonal term is the 2-point function. The diagonal term is the 2-point function at 0 lag. So it is sigma squared is 0. And so if we want the so we want psi, which is just going to be the integral of delta 1, delta 2 in the log normal process integrated over the probability distribution. And so we have delta 1 and delta 2 as exponentials. The Gaussian has an exponential. You can solve this. And you get a very nice relation that the 1 plus the correlation function is just the exponential of the correlation function of the generating field. So this is beautiful because it can be inverted. If you have some target correlations here, you can deduce the correlation function and hence the power spectrum for the generating Gaussian field, and you can make log normal realizations very quickly. Fully consistent, positive density, highly nonlinear with the desired power spectrum. And you can now write down within this model, I think, quite informative models for as an example of this sort of nonlinear local bias. So suppose, for example, that I said that the galaxy density was some power of the mass field. It's then easy to show in the log normal model that the 1 plus the galaxy correlation is 1 plus the mass correlation to the b squared. So of course it gives you linear bias in the sense when psi is small, you would have b squared times the mass correlations. On the small scales, it does something different. And if you define scale-dependent bias to be correlation function of the galaxies divided by the correlation function of the mass, square rooted, then you see that this rises to small scales. Okay, because the bias will be large where the correlations are large on small scales. And this, okay, that's just in a simple model, but it's actually for an underlying Gaussian generating process that's completely a general process. Whatever you think this local bias function is, the bias has to be monotonic with scale. So, yeah, so and that's the point. Please remember that, because I'm going to come back to that quite shortly. Because historically, this was a big puzzle, basically because the data looked as though it needed a variation with bias that wasn't just a simple monotonic variation with scale. All right, let's turn now. I mean, the advantage of what I just showed you was that it's completely general, but then that's useless. You don't have a theory of what this function should be, and you'd rather have some understanding of where bias comes from. And as we heard in the previous lecture, the key breakthrough for this was made 35 years ago by Nick Kaiser. And like all great ideas, it's quite obvious in retrospect. What he said was that you're only going to form complex structures in the universe where gravitational collapse can become nonlinear. And so we heard that is going to happen where the density fluctuation, or rather the linearly extrapolated density fluctuation, reaches this threshold of about 1.7. And that comes from the spherical overdensity model. So your picture should be of some fluctuating density field, and only the parts within it that exceed this collapse threshold are going to be able to form nonlinear structures. And you can see just by your eye that if you have some long wavelength component of this field, the effect of that component is amplified. It only produces structures where the long wavelength component peaks. And you can analyze this very straightforwardly. So let's assume that the density field is Gaussian. This is all applying on large scales. What's the probability of lying above some threshold in a Gaussian process? Well, it's the error function, but that's dominated by an exponential term, which is, actually this is a terrible font. This thing that looks like V is a nu. So this symbol nu is the threshold in units sigma, sigma being the overall RMS of the density field. So you're asking how this exponential probability will respond if you perturb the density by adding in this long wavelength disturbance here. Let's call it epsilon. So we can differentiate this probability with respect to nu as we change the threshold delta C. So fractional change in probability is just nu d nu. And that is, it's nu, the change in nu is just epsilon, the long wavelength term, divided by sigma. So we've now got nu over sigma times epsilon. So nu on sigma is the bias. So that very simple formula was revolutionary because it led you to understand how rare objects in the universe should be very strongly clustered. Now, let's clarify something. This is what we would call Lagrangian bias. Lagrangian coordinates, again, were mentioned earlier. They're just coordinates that specify the initial positions of particles. So all we're doing is saying that there are regions of space on some uniform initial grid, and some of these are lit up by clustering, by being above the threshold in terms of the linear density field, but then they undergo gravitational displacement. It's the same argument I gave you when talking about the gravitational driving of bias according to Jim Fry. And all this does is add a constant to B. That is, if there was no Lagrangian bias at all, no Lagrangian clustering at all, if the original objects were uniformly distributed, the displacement field drives things to be clustered the same as the mass. So what you should do is add 1 to this Kaiser nu on sigma. All right. Now, an important point to emphasize is that this paper is one of many classic papers in the literature which is much cited and never read. I bet quite a few of you had heard of Kaiser 1984, yes? Let's have a show of hands. How many of you have actually read that paper? Right, good. Okay, keep your hands up. Of those of you who've actually read it, how many think that this paper introduced the idea of biased galaxy formation? Well, it's a common, you will see Kaiser 1984 cited as introducing biased galaxy formation. It didn't. What he was interested in was understanding the problem that massive systems, Abel clusters of galaxies, showed a very high amplitude of the two-point correlations. And the reason they do that is that mostly Abel clusters are still forming. They're rare mass fluctuations in the universe today. So their typical density fluctuation is low compared to the threshold of 1.7. But galaxies formed long ago, mostly. So they aren't rare objects. So this mechanism would never explain why galaxies would be biased in a way that was different from the mass. But what happened was that 2 years later, Bardeen et al., 1986, a famous and intimidating to this day paper, suggested that there could be a non-gravitational threshold, that for some reason, unknown at this time, galaxies only formed in regions where the density field took a high value. Then you could use all this apparatus to say that galaxies would be highly biased. The reason they wanted to do that was that in those days, everybody was convinced that we lived in an Einstein de Sitter universe, that the matter density parameter was 1, lambda was clearly 0, and basically from the microwave background, there's a problem that the mass density fluctuations that match Einstein de Sitter universe require a relatively low normalization. So you compare the low normalization of mass fluctuations with the high observed galaxy clustering, you need a high bias. So Bardeen et al. Realized that a non-gravitational threshold would close this gap. So this was a great paper. It still is a great paper, but it destroyed cosmology. It sent us in a completely the wrong direction for a decade. because everybody was convinced that we could make this model work, and of course it was wrong. And we would have realized it sooner without this. Okay. So let's then move on with this, this foundation of the ideas of the statistical approach in the Poisson clustering model and biased galaxy formation to testing the basic framework for mass fluctuations, that is the cold dark matter model, which of course was first set up in the very early 1980s, really before galaxy clustering data were particularly good. But let's just remind ourselves what the different ingredients that the CDM model offers are. The dimensionless power spectrum tends to look like this. That is, it's of some power law, which then breaks to a flatter power law at small scales. And that break scale, I'll say some more about its origin shortly, but empirically, for now, let's accept the fact that it depends on the density of the universe, and it moves to larger scales for low-density universes, and it depends on the combination of the matter density parameter times the Hubble parameter. You can also change the slope of the primordial large wavelength spectrum. That's the scalar spectral index that comes out of inflation or whatever generated initial conditions. And you can have a pure CDM universe, which this is, or you can have an increasingly large fraction of baryons. And then you see the infamous baryon acoustic oscillations, about which I'll say more tomorrow. Worth mentioning that we also talk a lot about the normalization of the power spectrum in terms of sigma 8, and that is sigma 8 squared is the variance of the density field when we convolve it with a ball whose radius is 8 h to the minus 1 megaparsecs. All right. In the early days, you might think all you've got. So, from what I just said, you might think all you've got to do is to take these theoretical lines, put some data points on top, and make the comparison. That wasn't so easy in the early days because there were no three-dimensional surveys. Everything that came from galaxy data was just seen on the sky without redshifts. So I should say a few words about dealing with projected clustering. So let's imagine that you have some projected density fluctuation that's a line integral with co-moving radius of the 3D disturbance times some kernel. Now that kernel can be simple if you're just talking about the distribution of galaxies on the sky. It's just proportional to the number density, the number of galaxies you have in a given redshift range. Or it can be more complicated. Here's the expression, which probably you should have seen in Alan Heavens' lectures, involving not only the distance, but also the distance to the last scattering surface. Actually, no. So this is the kernel for the optical depth gravitational lensing. But actually, I've got it specific here to lensing of the CMB. But actually, this RLS should be just whatever the radius of the background objects that are being lensed is. So depending on what the physical application is, there'll be a different kernel in here. In any case, once you've got your projected field, you would expand it in angular terms, as you know, some expansion coefficients times spherical harmonics. This is all completely analogous to flat space Fourier expansions. And so there, the two-point angular correlation function is 1 over 4 pi because of the normalization of spherical harmonics. It involves the Legendre functions. And CLs are things you see a lot. What are they? C sub L and the expectation value of the modulus squared of the ALM coefficients. All right. If you remember one thing from these lectures, I would like it to be this. The correct symbol for the two-point angular correlation function is lowercase w. And I see lots and lots of papers where it's written as small Greek omega, and it isn't, okay? So please don't make that mistake. You would like to be able to relate this projected two-point statistic to the three-dimensional two-point statistic. How can you do that? Well, if you want the two-point function w theta, it's basically the projected, you're now just projecting along two different lines, and you want how these two projections relate to each other, given that points along the line have a three-dimensional correlation, psi of r. So you just need to multiply this thing together twice, and then usually, not always, but usually you can use a thing called the Lambda approximation, where you would say that the scale over which the correlations are non-zero is small in cosmological terms. It's tens of megaparsecs as opposed to gigaparsec baselines. So the correlation, the integral only matters where the two radii are more or less the same. So you just end up, rather than with two different kernels, the square of the kernel at the same radius, and now you're integrating over the two-point function. You can express that in Fourier space just by putting in the relation between the two-point function and the power spectrum, and that brings in a zero-order Bessel function. Neither of these expressions, although they're very common, are the ones you should actually use. And the reason for that is that there's two integrals here, one over distance and one over scale. But Nick Kaiser realized that if you work purely in harmonic space, you get simply a one-dimensional integral. So the angular power spectrum is basically, and this is also physically informative, you can see it's just a smoothed version of the 3D power spectrum. So it's a single integral over distance, and it brings in the 3D power spectrum at a wave number, which is the angular wave number divided by the distance. And it's easily generalizes. I've written it here for cross correlation. So if you're after the cross power between two different fields on the sky, so for example, you would use this if you wanted to analyze the cross correlation between projected number density of galaxies and CMB lensing, for example. So historically, this was important because we didn't have distances. Even today, when we have distances, we tend to have imperfect distances. So often the redshift is estimated photometrically. So what you'll find is a field that's called tomography, where the galaxy field is split into a number of bins, let's say 5 to 10, covering redshift 0 to 1, defined by the photometric redshifts. But you can still use this formalism to ask how all these bins are cross-correlated with each other. Okay, so that was the technology. So probably the first experiment that powerfully exploited this was the Cambridge generation of the APM galaxy catalogue. This is from photographic plates. Here are their angular clustering. Different lines here show you samples of different depths. I mean, basically, if you take a relatively shallow cut, just the bright galaxies, they have quite strong angular clustering. If you go fainter, you push them further away, it pushes things to smaller scales and also dilutes the amplitude, and so the faintest galaxies are down here. But because you have the projection formula I just showed you, you can say what that shift should be and show they're all consistent with a single angular clustering. And you can compare that angular clustering by the Lambda formula to 3D power spectrum, assuming linear bias, that the shape here is the shape of the matter power spectrum. And what was found was that the omega h parameter, the characteristic break scale in the power spectrum, had to be at a low value, too low to be consistent with an Einstein de Sitter universe. And at the time, this already allowed us to infer the universe had to be lambda dominated. This is 1990. So let me... okay. So let me try and enlarge on that and then probably stop. Where does this break in the power spectrum come from? It has the same sort of origin as the structure that you see in the microwave background. And all these relate to length scales in cosmology, which come from horizons. So what is a horizon? It's just the distance that signals can propagate, light, typically, but you can also talk about the acoustic horizon if you're interested in sound waves. In any case, the horizon, the co-moving distance, is just, it's the physical length, CDT, but you scale it by the scale factor to get the co-moving distance, which you can also write as integral over redshift, with the redshift-dependent Hubble parameter. And that's very nice because you can then use the Friedmann equation, which relates to the current H naught according to what's in the universe. So, for example, the constant vacuum density plus moving matter A minus 3 plus radiation A to the minus 4. So the horizon sizes can be worked out and they involve the cosmological parameters, particularly the matter density. So if you do this at matter radiation equality, you find a horizon size of 16 megaparsecs. You do it at last scattering, where the CMB comes from, it's a couple of hundred. You do it today, it's about 6 gigaparsecs. And the interesting thing is, particularly for today, scaling with the density parameter is quite different depending on whether you have a flat universe, that is one where the matter and vacuum densities add up to 1, or whether it's open, that is, there's no vacuum density, which is what everybody would have assumed prior to 1990. So the break in the CDM power spectrum we see is this scale, and the 1 degree scale, the fact there are 1 degree patches on the CMB sky, is really the horizon size at that time divided by the distance today. Now that's interesting because that angular scale, therefore, would be basically independent of the matter density in a flat universe, right? Omega matter to the minus 0.5 as opposed to minus 0.4, but it has an omega matter to the 0.5 dependence if there's no lambda. So basically, what you're seeing is that the CMB knows about the cosmic geometry. That is, you take a flat universe and you make it open. Wait a minute. You take an open so you take a flat universe and make it open. Everything, all the structure shifts to smaller scales. And so even before the CMB had any structure detected in it, there were severe upper limits on the small-scale CMB fluctuations. And so it was known that this was impossible. And there was a very nice paper in Nature in 1990, which really deserves to be read by anybody who's interested in the history of this subject, making this argument, completely watertight case. Large-scale clustering from the APM survey told us that the overall matter density had to be low. The CMB tells us that it can't be low and heavily open. The only option, therefore, is to add in a positive cosmological constant. And nobody believed it. That was partly because the data were not unequivocal. At the time, you would find papers from using the supernova Hubble diagram. This Perlmutter et al. 1996, they don't want you to remember this, but this paper firmly excluded lambda-nominated models. So in the mid-1990s, everything was very confusing. There was this good argument, nobody wanted to believe it because a non-zero lambda was crazy. Other arguments said that in any case, it didn't work. was only in 1998, when the supernova people realized their mistake and everything pointed towards Lambda, that the field accepted that the current cosmological model had to be the correct one. All right, so thereafter, things moved quite quickly. We had the 2DF Galaxy Redshift Survey. Thank you. Is that all you're going to say? I am nearly finished, honestly. Which gave us the beautiful picture of large-scale structure I started with. That gave us the ability to measure accurately the three-dimensional power spectrum directly. So here are the points contrasted with CDM lines. So just let me say a couple of things. The different lines show you different quantities of baryons. And you can see directly that this is not a baryon-dominated universe. Where are the large acoustic oscillations? There's a hint of something small in there. But that tells you that the baryon fraction has to be subdominant. Indeed, you can fit the data, and you've got a baryon fraction of a bit under 20%, which is exactly consistent with other inferences, say, from Big Bang nucleosynthesis or the CMB. So this was 2001. This was the standard model of cosmology as we have it today. And really, you might say the only thing that's changed in virtually 20 years is that we now know, thanks to WMAP in 2006, that the primordial spectral index isn't quite n equals 1, which is a historically important achievement. But nevertheless, 20 years ago, we were basically very close to where we are today. All right, that's probably a good place to stop. I think formally that allows some time for questions, which you can either have now or come and chat to me afterwards. Silence. They all want their lunch. Yeah. Yes. Okay. There was a question about where does angular selection come into the Fourier methodology. And this raises the whole issue of how you cope with a survey mask. So you can set things up so that you know how you would analyze a cubic volume of space. What do you do if part of that isn't surveyed? And so obviously on the whole sky, there are low galactic latitudes are cut out for sure. In practice, who knows what other complicated geometry there may be. So you can think of that, and within whatever region of sky has been surveyed, then you have some selection in redshift. So overall, what that's doing is basically replacing the density field by something which would be called the window. And you have to ask, well, what does that multiplication, this removal of signal outside places where the window is non-zero, do to the properties of the density field? And the answer is, well, it's pretty obvious. Excuse me. If you take the Fourier transform of that, that's a convolution. You want to know what happens to the power spectrum. You can't just put modulus squared around these two terms, but you can if you make the assumption that the mask is unrelated to the density field itself, if they're uncorrelated, which it might not be. There's, for example, there are some tricky questions. Suppose in here there lived a bright galaxy. Well, you can't find the faint galaxies behind it. Right? So sometimes you have to exclude such regions from the survey. And that means that the survey mask is coupled to the density field to an extent. But if that's not the case, if the mask is just defined, let's say, by the position of bright stars or whatever, then the power spectrum that you're inferring is the true one, the one you want to know convolved with the power spectrum of the window. And that, I didn't say, but in 2DF, that convolution has been allowed for in dealing with the data. Okay, seems we're done.